Good morning and welcome to our series of lectures on special theory of relativity. This is the second lecture on the series. In the first lecture we have found, we have studied Maxwell's Michelson-Morley experiment, in which we found that the ether is, according to Michelson-Morley experiment, there is no such thing as called ether. So when there is no ether, it means now light travels without any medium, because there is no such medium through which the light propagates. This was experimentally proved. The existence of ether was experimentally disproved by the Michelson-Morley experiment. So now the null result of the Michelson-Morley experiment to detect the drift of the earth through the ether can be understood by making a revolutionary change our thinking. The new principle is, so the idea that there is no ether led Einstein to propose two theories. One is that since the space is isotropic, the fundamental laws of physics must be same in all reference frame. And number two is that the speed of light is constant in all reference frames. These two theories proposed by Einstein, which is the foundation of our special theory of relativity. So the special theory of relativity is this special theory of relativity. The null result of the Michelson-Morley experiment led us to detect the drift of the earth through the ether. Can be understood by making a revolutionary change in our thinking. The null result of the Michelson-Morley experiment to detect the drift of the earth through the ether can be understood by making a revolutionary change in our thinking. And the new principle is, the new principle is number one. Since the space is isotropic and uniform, space is isotropic and uniform. Isotropic means on the left hand side and the right hand side give the same results. Whether you left side, right side, front side, back side, the space is isotropic, the same, and uniform. The fundamental laws of physics are identical. laws of physics. Are same for any two observer in uniform relative motion, in uniform relative motion. In uniform relative motion, when the two observers are moving relative to each other uniformly, the laws of physics must be same in both the reference frames, because the space is isotropic. Isotropic means everywhere, the left hand side or right hand side, the laws will be the same, the space is same. So if you measure, two observer measures which are in relative motion, they will observe the same laws of physics. They will and number two is, this is the first principle, and the second is that the speed of light is independent of the motion. The speed of light is independent of the motion of the light source or the observer. What does this mean? This means that if this is a light source and here is an observer, this is observer and this is the source. If the source and observer are at rest, the speed of light which will be absorbed by the observer will be say c. Now if the source is moving towards the observer with velocity v, according to Galilean, the speed of light to the observer must be c plus v, but not. But according to this principle, the speed of light will again be the c. It will not c plus v. Or if the observer is moving, whether towards the source or away from the source, still the speed of light will be the same. It will not, we suppose the source of since the c is 3 lakh kilometer per second and the source is moving with say 1 lakh kilometer per second towards the observer, it doesn't mean that the light will received by the observer will be c plus v, that is 3 plus 4 lakh. No, it's again the 3. This is the meaning of this. And if the observer is moving away, it doesn't mean that 3 minus 1, that is 2 lakh kilometer per second, but still the light that will received by the observer will be 3 lakh kilometers. This is the meaning of it. The speed of light is independent of the motion of the light source or the observer. So these two revolutionary statement was given by Einstein. The first one was that the laws of physics will remain same because the space is isotropic and uniform. So there must not be any change in the laws of physics, and the speed of light is constant. This is the due to the experimental evidence provided by the Michelson model that there is no ether as such. So now we will do some transformation. Suppose that one reference frame is moving and the rest, another one is at rest, and how the laws of this is transformed from this frame to this frame, which is according to relative to S frame. This is moving with a certain velocity. How the position changes from S frame to S dash frame. The transformation relation we will do, and that is called the Lorentz transformation. Lorentz transformation. Now let us have two reference frames. S and S dash. This is S dash, this is S, and suppose this is the origin of this reference frame, S frame. This is the origin of this reference frame. This is say O dash. The coordinates measured in this reference frame is say X, Y, Z at time t, and the coordinates and time measured in this reference frame is X dash, Y dash, Z dash, T dash. Now suppose a light is flashed here, and the light is flashed here also at the same instant. The light pulse moves. At the same time the light pulse moves here, and since the speed of light is same, the distance traveled in time t in this frame will be ct, and the speed, the light pulse which is traveled in this S dash frame in time t dash will be ct dash. So let us have two reference frames, S and S dash. If we flash a light, if a flash of light is emitted as two observers pass each other, in the two reference frames. Each think of himself to be at the center of a uniform expanding spherical wave front. So what's the, it means if suppose that this frame is moving and the light is flashed when they pass each other, when they are at the same point. This was actually the same, now it has moved. At the same instant, then the light was flashed. But now each observer will think that a wave front is moving spherically outside. This also will observe. The wave front will, light is flashed here, the wave front will spherically out. In the same way, the observer here will think that the wave front is moving spherically. So this is written. As the two observers pass each other in the two reference frames, each think himself to be at the center or in form expanding in spherical wavefront. The light was flashed and emitted the two frames. Okay. Now now since the light is flashed here, so the light will move in a space. So the distance that will be traveled will be x square plus y square plus z square, and is equal to r square. R square is equal to c is the speed of light and t is the time taken. So it will be equal to c square t square. If in the three dimension, the radial vector will be x square plus y square plus z square, and this radial distance is covered in the time t with speed of light c, so it will be ct. So it is similarly like r square is equal to x square plus y square plus z square. So this is the equation of wave front as seen by observer in the S frame. The observer is here at O. So the equation of the wave front as seen by the observer at the origin of S frame will be x square plus y square plus z square is equal to c square t square. Now the same of in the S dash frame, the observer is here, and we find that since the speed of light is same in both that the observer in this the equation for the wave front in this frame will be similarly the equation for wave front as seen by an observer in S dash frame will be, since the coordinates in this S dash frame is x dash, y dash, z dash, and time measured in t dash. So this will be x square z square plus y dash square plus z dash square is equal to c square t dash square. It is c square t dash square. This is the equation. Since both the observer are at this origin of their expanding universe, this equation must be same. So equation 1 and 2 must be same, because For them, the speed of light is traveling in that time t dash is c. This is this question. Since both the observer is at the center of the same expanding wave front. Question 1 must be equal to question 2 because the wave front was the same. Just as you have passed, the light was flashed. So the wave front which is observed here by the observer here will be given by this equation. And the same wave front, since the wave front is the same as observed by this frame, will give you this simulation. So since the wave front is same, these two equations must be same. So it means now since this wave front is moving with velocity v, so there will be there is a relation between x dash and x. Since the velocity is moving only along x-axis and y and z remains same, so this x dash is s dash is moving relative to s with uniform velocity v along the x-axis. So x dash must be equal to x minus vt and y dash is equal to y, z dash is equal to z, and time must be the same in both the frames because time remains same in all reference frames. So t dash is equal to t. This simple Galilean transformation means suppose you are moving with if you are moving there, so if this is x dash and this is x, so x will be equal to x dash plus this distance, and this distance is if it's moving with v velocity, this is equal to v t. So x dash is equal to x minus vt. So this is simple. Because if this is the distance measured relative to this frame and this is the measured relative to this frame which is moving, so in t time this frame must have moved by this distance vt. V is the speed of light, is the speed with which s dash is moving, and t is the time taken. So this is the distance vt. So x will be equal to, or x dash will be equal to x minus vt. So this. Now since there is no motion along y-axis and z-axis, so y dash will be same, z dash will be same, time is same. This is called simply Galilean transformation. So if we apply Galilean transformation, now, and we have seen that in equation 1 we have x square plus y square plus z square is equal to c square t square, and x dash square plus y dash square plus z dash square is equal to c square t dash square. These must be same. So if instead of writing x dash, we want to transformation between these two. So in place of x dash, we use x minus vt, and y dash will be pi, z dash is equal to z, and t dash is equal to t, and see if both are same or not. So substitute in this was our equation 1 and this was our equation 2. Substitute in equation 2 this transformation. Substitute the above Galilean transformation. In question 2 and see what happens. If you substitute this, you will get, instead of x dash square, you get x minus dt whole square. Y dash is y, z dash is z, c square t square. If you open this, it will give you x square plus y square plus z square plus this b square t square minus 2x b c square. This obviously is not equal to equation 1. If you use this transformation, this extra term, this is the extra term which comes in. If this is true, then these two equations must be same, and the transformation, you use this transformation, Galilean transformation, the result must be same. But if we have substituted this transformation, we got this extra term, and this is the extra term, and this is due to the velocity of the reference frames. This could be equal to this equation only when v is negligibly small. If we neglect the v in relative to c, the value of v relative to c, because v is the speed of the reference frame. If v is very much less than the speed of light, then this value and this value will be negligibly small. This can be removed and we get the same result. But if the reference frame is moving with higher velocity or speed comparable to the speed of light, this term cannot be removed. It means we have to seek for another type of transformation which retains this value. Retains the transformation. No. Because according to Einstein's first principle, thus laws of physics must be same. So we are in search of another type of transformation, and let the transformation is equation 3 is obviously not equal to equation 1. This can be equal to equation 1 only when v is very much little. Equation 3 could be equal to equation 1 only when v is very much less than c. So this can be negligibly small, we can remove this term, then only we can say that 1 and 3 are same. So we now seek for transformation which retains the same. Let the transformation is the type. Let the transformation is x dash is equal to some constant term x minus. This is the earlier we used x dash is equal to x minus vt as transformation. The Galilean transformation. Now we take a new term here, which is called gamma as constant term, and assume that let the transformation is of this type, where gamma is independent of space and time. Gamma is independent of space and time, but varies with velocity. So we assume that there is a constant term in between them, and that constant depends only not on space and time, but only on velocity, where gamma is independent of space and time, but vary with the speed. Now, when we write x dash is equal to x minus vt in Galilean transformation, we could even write x is equal to x dash plus vt. Call the inverse transformation, whether you measure from this reference frame or this reference frame. So the inverse of this will be x is equal to gamma times x dash. Gamma remains same in both because the space is constant. So now we have to find the value of gamma. Our aim is to find the value of the gamma, which we have introduced as a constant term here for the transformation. So our aim is just to find the gamma, and that gamma will leads us to the transformation from one frame to the another frame, where gamma is independent of the values of x and t, but depends only on the velocity, relative velocity between the two frames. Okay. So here x is equal to gamma x dash plus b dash. Now x dash is x minus vt. We can substitute here. X is equal to gamma x minus vt plus b dash. This can written as, you can open the bracket and bring this on this side. So this comes up to gamma vt dash is equal to gamma times x minus vt plus minus x. Oh. Okay. Sorry. X dash is equal to, x dash is equal to gamma times, so it is here, gamma times, because x dash is equal to gamma times x minus vt. So x dash is equal to gamma, this gamma is here, so it will be gamma square here. So it is gamma v t dash is equal to gamma, or say take x as common, and gamma square minus 1. Gamma square x minus x, taken x out, gamma square minus 1. This is equal to minus gamma square vt. Something is, we have taken this on this side, so it will be minus here. This is gamma vt dash, we have taken on the right side, so it will be minus, and this x on this side will be minus. It's alright. Now if we take this as positive, this will be as negative, this will be as positive. Okay. So take t dash, divide by gamma v, so this will be gamma times t plus minus x gamma square minus 1 by gamma or you can write it like as the same way writing. Okay, you can write this as 1 minus gamma square by gamma v. Let's suppose this is equation number 4. Okay, now the light pulse in x frame, the x component of the light pulse x frame will move in time t, c into t, speed of light of time taken, and the same light pulse which moves in the moving frame, the distance measured in that frame is x dash to x c t dash. So the same light pulse which travels in the S frame moves the distance equal to x component, the distance equal to ct, and x dash component ct dash in the moving frame. So now the x component of the light pulse in S frame is x equal to ct, and that in S dash form is x dash equal to c t dash. So c dash is equal to c t dash. Now x dash can be written as gamma times x minus dt, and t dash is this, t dash in terms of t and x dash in terms of x in this. So substitute here, we'll get gamma x minus dt c, and t dash is this value from equation 4. So this will be equal to gamma t plus x times 1 minus gamma square gamma v substitute this value, this is gamma t plus x times. So this. Now you open the bracket on those and some term will cancel out. So it will be gamma times x minus gamma times dt. C gamma t plus cx 1 minus gamma square by gamma v. Take the x component on the left hand side and t component on the right hand side. So it will be gamma x minus c, or you can take x at okay in the next term you will write like that, gamma c t, take this on the right hand side, it will be equal to gamma dt. Take x as common, you will get, or you can take gamma out also, x and gamma both also. It will be 1 minus x is taken out, gamma is taken out, but there is no gamma here, it will be gamma square here. So it will be c times c by v 1 minus gamma square by gamma square. Here we take gamma out, it will be equal to ct plus v. You can take t also, c plus v, t is the commutator also. So this gamma and this gamma cancels out. Now this is x and 1 minus c by v, 1 minus gamma square by. You take c outside from this side bracket, so it will be c t, 1 plus v by c. Now we know that x is equal to ct, so this ct and x cancels out. Now we have to find the value of gamma. This can be found out from this. Okay? This is 1 minus c by v, 1 minus gamma square by gamma square is equal to 1 plus v by c. This 1 cancels out. Or you can write 1 minus absorbed inside, this will be c by v gamma square minus 1y gamma square is equal to v by c. You can write this 1 minus 1 by gamma square. So, gamma square by gamma square will be 1, and this v square by cross multiplied this. Now 1 by gamma square. 1 by gamma square will be, take 1 by gamma square on the right hand side, v square minus 6 on the left hand side, you get 1 minus v square by c square, or gamma can be as, take this in the numerator side, this one, so 1 minus v square by c square, inverting. So this way we have found out the value of gamma, and the gamma depends only on this relative velocity and not on the space and time. Does not depends upon x, y, z or t, but it depends only on the relative speed within the two reference frame. So if you substitute this value of gamma in our transformation equation, which we have proposed as a new transformation equation, in that case we get, substituting this value of gamma in the transformation equation, we get our transformation equation was this gamma x plus x minus v. So substitute here, x dash will be equal to x minus vt 1 minus v square by c square. It means that now the transformation is of this type and not in the Galilean type, x dash is equal to x minus vt. This will be the of Galilean type only when if v is very much less than c, then this transformation will become Galilean type. So this we observe in our daily life this type of transformation only because our reference frame moves, the velocity of our reference, the velocity of the relative velocity of our reference frame is very much less than the speed of light. That's why we observe only this type of transformation. But if you assume that the reference frame is moving with speed comparable to the speed of light, this transformation will not work. You have to work in this type of transformation. And this inverse transformation will be the inverse transformation. X is equal to x dash plus vt 1 minus v square by c square. Now transformation about time. Because in equation 4 we have found that time t dash is related to t and x by this type of relation from whatever that equation I wrote that, but I am writing that equation that t dash is equal to gamma t plus x 1 minus gamma square by gamma t. This was the relation between t dash and t and x. So this is gamma t. You take gamma out as a common plus. If you take gamma out, there is no gamma here. If you are taking gamma out, gamma will be divided. gamma square, this term will be gamma square. So it will be 1 minus gamma square by gamma square. Oh, there will be also. Or write this as gamma t plus x by v 1 by gamma square minus 1. Now, what is 1 by gamma square minus 1 is equal to 1 by gamma square means 1 by v square minus gamma square is gamma is under root by minus v square by c square. This we have worked out. So its gamma square will be 1 by 1 minus v square by c square, squaring both sides. So if we invert, this will be equal to 1 by gamma square is equal to 1 minus v square by c square. So if we take v square by c square, this is equal to 1 minus 1 by, taking this on the right hand side, left hand side, this on the right side. So this is 1 minus 1 by gamma square. You can take gamma minus sign x by v is equal to 1 minus 1 by gamma square. And 1 minus 1 by gamma square is going to be square by c square. So it will be gamma times t plus t minus x by v, and this term is v square by, so 1 v cancels out, we are left with gamma times t minus x v by c square. So t dash is related to t by this when gamma is known. So if you substitute the value of gamma here, the transformation equation for time will be t minus x v by c square, and the value of gamma is under root 1 minus v square by c square. So this is our relation for time. So the in general, if you substitute, write all the transformation, that is x dash is equal to x minus vt 1 minus v square by c square. Since there is no motion along y axis, so the y dash is equal to y, z dash is equal to z, and t dash is equal to t minus vx by c square 1 minus v square by c square. So this is our new transformation. This is called Lorentz transformation, and the inverse transformation will be only plus sign here. So the inverse transformation, inverse transformation will be x is equal to x dash plus vt 1 minus v square by c square. Y will be equal to y dash because there is no motion along y axis and z axis, and t is equal to t dash plus vx by c square 1 minus v square by c square. So these new transformation would lead us to a very interesting situation where the length and time are different in two reference frames. The times are same only when this v term is 0 or very small, then only t dash is t. If there is substantial value of v here, t dash is transformed like this equation. And this is called the Lorentz transformation. And in the next class we will see the consequences of the Lorentz transformation. Okay, I am leaving this for the next class, the consequences of Lorentz transformation, which lets us to that there is a time dilation and length contraction in the two reference frames. When measured, two lengths are measured into the same length are measured in two different frames. The lengths are not the length are not is measured in one frame will not be equal to that measured in the another frame. Similarly, the time which is measured in one frame is not equal to the time which is measured in the next frame. So these are the consequences of this Lorentz transformation, and the next class we will study that part. Okay, thank you.